Okay, so this is going to be my recording for going through the week 2 slides because last week was very rushed towards the end a lot, and we had technical issues in one of the classes. So I'm going to go through the slides kind of just at a casual pace. So feel free to pause the video, go back, slow it down, change the speed of the video, speed it up if you want. Skip around and go back to it. But I'm going to go through all of the slides here, all together, all in one go here. So let me share my screen. Let me go back to the first screen. Okay. So week 2 slides. And we're talking about fractions, mixed numbers, which kind of goes in hand with the fractions, and decimals. So definition of fraction. So fraction is when we have a whole unit divided into equal parts, and we're going to call that a fraction. And so what we mean by this, a fraction is made up of 2 parts, the top and the bottom, right? Fractions written in the form a over b, right? Oh, and keep in mind one thing, I'm writing with a mouse, so not everything's going to be super neat. So we've got the top and the bottom, and in this case, right, the a over b, top and the bottom. The bottom is what I'm going to start talking about. First, the bottom, this is called the denominator. Okay, the denominator, and I'll go back and forth between using denominator and the bottom of the fraction because it's easier to understand what I'm talking about when I just say bottom, but out of habit, I will call it denominator a lot of times. So the denominator tells us how many equal pieces something has been split up into. Okay, so with this circle here, we can see, ignoring the shaded and non-shaded parts for a moment, the circle has been split up into 3 equal parts, right? 1, 2, and 3. So if we have a fraction that represents this circle, it will have a denominator of 3. The bottom will be 3. The top of the fraction is called the numerator. And the numerator tells us how many of those equal parts that we have, right? So if we have something that's split up into thirds like the circle, and the shaded regions now are what we have 2 of those thirds, right? We have this one and this one. So as a complete fraction here, right, finishing it out, I have 2 out of the 3 parts of the circle. So to represent this circle as a fraction would be 2 over 3. The numerator is 2, the denominator is 3. All right, so some properties of fractions, and I'll go through all of these. I kind of skipped through some of them last time. I'll go through all of them. One thing to keep in mind here is a fraction is just division, right? So with this first number 1 here, a over 1, a fraction is just division. So a over 1 is just a divided by 1. Anything times or multiplied or divided by 1 will always just be itself. So like 2 times 1 is 2. 35 times 1 is 35. And the same thing goes with division. So like 35 divided by 1 is 35. So anything divided by 1 is itself, and a fraction is just division. So anything over 1 is just itself. It's just a in this case. So with the example as -8 over 1, this is equal to -8. And this property is very useful too, because we'll see a lot of the time that we'll want to, we like to do math in fractions, and sometimes we don't, we just have a number, I don't know, 25, and we want to turn it into a fraction. And the easy way to do that is just put it over 1, right? Putting it over 1. Dividing it by 1, which doesn't change 25, the value of it. So 25 over 1 is the same thing as 25, right? Because anything divided by 1 is itself. Here. The next part here is when the numerator, when the top is 0. Okay. The top is 0, number 2. This is always equal to 0, no matter what the bottom is. 0 over 27, that's always 0. And we can think about this in terms of how we define what a fraction is, right? If something's been split up into 27 equal parts and you have 0 of them, you have nothing, right? You don't have anything. So it's just 0. So 0 divided by anything is going to be 0. This comes up specifically when we're changing improper fractions to mixed numbers. So we'll talk about that in one of the examples. We'll see that when that pops up. A over 0 is undefined, number 3 here. A over 0. You can't divide by 0. This is, it's undefined. What I'll say about it is it's not going to come up in any questions. You're going to be asked to find A over 0 and tell me that it's undefined. But it's useful to know that if you end up with 0 on the bottom, you have gone wrong. Something's gone wrong. Something has gone wrong. We can't divide by 0. And that's just like a universal math rule. That doesn't ever really change. So that's all it is there. It's just kind of a warning. If you've somehow got to A over 0, you've messed up somewhere. A over A is 1, number 4 here. This is anything over itself is 1. So 5 over 5 is 1. And this is you can remember that fractions are division. So right, 5 over 5 is the same thing as 5 divided by 5. So that's 1, right? Anything divided by itself is always 1. 1/2 divided by 1/2. Even just two fractions divided by itself, it's divided by the same thing. So it's always 1. So anything over itself is 1. And this is useful for a number of things that we'll see. I won't always evoke this, but I'll try to bring it up. We're going to be canceling things out. We will be, it's also very useful in like the explanation of why some of the math is the way that it is. But a lot of times I'll skip past it, and it's usually because I can multiply something by 1 or divide it by 1, and that'll be rule number 1 telling me that I haven't actually changed anything, because anything divided by 1 is itself. And then I'll change that 1 into something over itself. But the important thing is anything divided by itself is 1. So anything A over A is always 1. B over B is always 1. The negative signs in number 5 here. Clear this off. Negative signs. We talked about in week 1, right? The multiplication rules when it comes to negative signs is that if there's an even number of negative signs, it's always going to be a positive answer. So if we remember that, right, that's an A, not a 9. Negative A over negative B. If I remember that fractions are just division, it's negative A divided by negative B. There's 2 negative signs, 1 and 2. So this is going to be a positive number. So if there's a negative sign in the top and bottom of a fraction, you can just get rid of them. It's going to be a positive number, A over B. Number 6, again, is dealing with these negative signs. And so you'll often see them written as, clear off. I'll just highlight it. You'll often see a fraction written like this, right? With this negative sign out front. And so with that negative sign, it can go, if it's out in front, it can go in the top or it can go in the bottom. And they're all the same thing here. And again, if the fraction is negative, it's because only one of them was negative. It's a division sign, so a negative times divided by a positive is going to be a negative number. So it can go in the top or bottom. It really does not matter where. Most people write it in the top though, and that's what I will do. So when I see something, a negative A over B, I will often just put it in the top, just because that's where I like to put it. You can put it in the bottom, but usually we want the bottom to not be negative, just for simplicity. So I always put it in the top. So improper and proper fraction. So these are the two main types of fractions here. So the proper fraction is just, so the difference between them is whether the top is bigger than the bottom or not, right? So a proper fraction is when where the numerator is less than the denominator. Okay, so the top is less than the bottom, right? So 2 over 3, 2 is less than 3. So this is a proper fraction. The top is less than the bottom. With improper fractions, this is always going to be less than 1. If I remember, 2 over 3 is just 2 divided by 3. I just plug that in my calculator, I get 0.6, a bunch of sixes here, and so on. So we have 0 point something. We are less than 1. So improper fractions are always, I'm sorry, proper fractions are always less than 1. And just the opposite then if the top is bigger, right? So what's the example? 4 over 3, the top, the numerator is greater than the denominator, the top is greater than the bottom. This is an improper fraction, right? Because 4 is bigger than 3. And improper fractions are always bigger than 1, right? So the proper ones are always less than 1. Improper ones are always going to be bigger than 1. So if I were to do the 4 divided by 3 like above, I'm going to get 1.3 in my calculator, a bunch of these. So we got a number bigger than 1. We got 1 and then some decimal points. And we can also see to see that this is more than 1 with our circles that represent fractions, right? When we were proper, we had just 1 circle and we didn't even fill it in all the way. So we had less than 1 circle. But when we were bigger in the top, we need to throw in another circle, right? So we've got circles split up into thirds, bing, bang, boom. But I've got 4 of them. There's only 3 here. 1, 2, 3. So I need another extra circle to represent that extra 1/3 that's split up into thirds. I've got 4 now when I do that. So 4 over 3. So mixed numbers. Mixed numbers aren't really fractions, but we're talking about it all together. Mixed number is a whole number plus a fraction, right? So 1 and 1/3 here. That's the same thing as 1 plus 1/3. And so as you can imagine, these mixed numbers are always going to be bigger than 1. If it's less than 1, you would just have, if it would have 0. How should I write this? If it were less than 1, your whole number part would be 0. If it was 0 1/3 is a mixed number, this is kind of weird because this is just you have nothing plus 1/3. So you wouldn't ever really write that. You would just write 1/3 in that case, in that made up scenario there. So mixed numbers are always bigger than 1. Improper fractions are always bigger than 1 as well. And so we have this idea of we're going to go back and forth between the two. Okay, we're going to go from first mixed numbers to improper fractions. Okay, and then we're going to go the other direction first after that. So mixed number to improper fraction. We're going to start the mixed number and improper fraction. We have this 1 and 1/3. And this way is pretty straightforward. You just do 1 times the bottom. You do the whole number times the bottom of the fraction part plus the top of the fraction part. That'll be the numerator. And then you keep that same denominator of what the fractional part was, right? So it's written out here, but I'll do it next to it, right? 1 and 1/3. I'm going to take 1 times 3, which is 3, plus 1, which is 4. That's going to be 4. And then we keep that same bottom, the 3, 4/3. And so this is that same example we've been seeing, right? That on the last slide, the 4/3, right? So 1 and 1/3, we have 1 full circle, and we have 1/3 of another one. But we also saw that with 4/3, right? If I have both of them split up into thirds like that, I have 4 of them. And this is the same shaded amount of area. So these are equivalent. This does represent that same amount that we have. So when I do this, it's just it goes between them really easy. So let's do the other one here. So if it's negative, honestly, you just kind of forget about it for a second, do the thing, and then throw the negative sign back in, throw it back in there. Uh, you can see that we just threw it out in front, put it in parentheses and put the negative sign out front. And so we changed the inside, and then that parentheses is still just out front. So I'm just saying ignore it, but it doesn't go anywhere. So it's just is always going to be negative. So let's see, 2 and 1/5. This is 2 times 5 plus 1. 2 times 5 is 10, plus 1 is 11. And then keep that same bottom 5. And it was negative, so it's going to be negative 11 over 5. So you got some practice ones. So with the practice slides here in this recording, this is where you might want to go back, see how I'm doing a little bit, because this might go a little fast because normally I'm waiting for answers, but I know how to do it. So this might go a little fast. So we've got this 3 and 1/2, convert the mixed numbers to improper fractions. And that is just the bit number, the whole number times the bottom plus the top. 6 plus 1 is 7, and we keep the same bottom too. Same idea. 2 times 8 plus 7. 2 times 8 is 16, plus 7 is 23. I'm going to double check that just to be sure. 2 times 8 plus 7, 23. And then 8 on the bottom. And again, one more time. 1 times 5 plus 1. 1 times 5 is 5, plus 1 is 6. Keep that same bottom. So this is the mixed numbers changing it into improper fractions. Okay, so now we're going the other direction. We're going the other direction, improper fractions to mixed numbers. So now we just have the fraction part where the top's bigger, and we're going to go into the mixed number one. We have the whole number plus a fraction amount. Okay, and this is just division, or long division, I should say, right? I believe most of us, if not all of us, has probably seen at least some form of long division. And so the way I always set this up, so I'm going to take the example here, right? 7/3, 7 over 3. I'm going to set this up into a long division problem. And the way I've always remembered is that the top kind of takes a little jump down. So I have 3 jump down into the box here, 3 divided by 7. And so now with long division, I'm going to ask myself, how many times does 3 go into 7? It goes in there twice, right? 2 times, because 3 times 2 is 6. And I'm going to subtract these. 1. And now this is where some differences between some long division methods are. When we're turning into a mixed number, we're gonna carry stuff down if there's stuff there. There's the other kind of one where we kind of just put a bunch of zeros and we keep carrying down zeros. We're not going to do that with this kind. If there's a number already in there, then we carry it down. If not, we're gonna stop. And so what's left here, this 1, is the remainder. So this is the long division with remainders. So it's 2 remainder 1. 7 divided by 3 is 2 remainder 1. And so this just tells us exactly what the mixed number will be. The whole number part, the big number part, will be the 2. The remainder is the numerator or top of the fraction part. And then we keep the same bottom again. Just like how with the other direction, we're always keeping the same bottom, we're doing the same thing. We're going to keep the same bottom. 2 and 1/3. And we could see how in this one here, 7 over 3, we needed 3 circles to represent 7 over 3 because we got 1, 2, 3, 4, 5, 6, 7 parts of circles that have been split up into thirds. But it's a little bit easier to see this as a mixed number, right? We have 2 circles, 1, 2, and 1/3 of another one. Yep. Let's go to the next slide. So again, another practice slide here. Slow it down, go back, repeat it again if you need to. 13 over 5, changing into a mixed number, long division. So 5, 13. How many times does 5 go into 1? No times. I'm not going to write 0 at the beginning. So now I'm looking at two numbers together. How many times does 5 go into 13? It goes in there twice because 5 times 2 is 10. 3. Nothing to bring down, so that's the remainder. So it is 2 with 2. The remainder is 3, and the bottom stays the same, 5. 2 3/5. 4 over 3. Setting it up. How many times does 3 go into 4? It goes in there once. Because 3 times 1 is 3. 1. Remainder 1. Nothing to bring down, so remainder 1. So this is 1. The remainder is the top, and the same bottom. 1 and 1/3. Now, 198 over 2. If you're quick on it, you can see that this is going to divide evenly. If you just type this in your calculator, 198 divided by 2, you'll see that it's even 99. That was it. If you don't see that, that's fine. We can do this same method. But we know that we should get 99. If I type in 198 divided by 2, I get 99. I know that I should have 99 as my answer. But suppose you don't see that right away. I'll show you how the other way to get to 99. And so we're just going to do that same thing. 192, the long division. 198, 9. I'm asking myself how many times does 2 go into 1? 0 times. It doesn't go in there. It's bigger. How many times does 2 go into 19? It goes in there 9 times because 2 times 9 is 18. Subtract 1, and now we finally have something we can bring down. So we have a number here. I'm going to bring that down. 8. So now I'm looking at 18. How many times does 2 go into 18? And again, it goes in there 9 times because 2 times 9 is 18. 0, nothing to bring down. So that's our remainder. Our remainder is 0 here. So building up the mixed number here, we have 99. Right, that's our whole number part, the 99. Our remainder is the top of the fraction part, and we keep that same bottom too. So I see 99 and 0 over 2. Now, remember, one of the first things about the fractions was 0 over anything is 0, right? 0 divided by anything is 0. So and one of the other ways is to think about how many parts of it we have. If we have something split up into 2 equal parts, I have none of those parts. I don't have anything. So 0 divided by 2, this is 0. I'm just going to cross it out. 99. I don't want to put 0 over 2 because that's just 0. So it's just 99, which if you saw the division right away, that's good, but that's not always immediately, obviously, and depending on the numbers. 99. Simplifying fraction. So so when we have a fraction, I did this last time. Okay, we're gonna talk about factors first, right? We're gonna build up to simplifying fractions. The first thing we want to talk about is factors. So if you have a number, I'll pick a different one and then we'll go through these ones. 25, and I want to determine whether another number is a factor of 25. Right? A factor is a number that divides it, the original number evenly, meaning that when we divide them, we're going to get a whole number, not a decimal or a fraction for that matter. So if I want to see if 5 is a factor, I'll write out the question a little bit, right? Is 5 a factor of 25? All I have to do here is take 25 and divide it by 5 and see what the answer is. In my calculator, that'll show me 5. 5 is a whole number. So that means 5 divided 25 evenly. So 5 is a factor, yes. So the answer is yes. So if I change it slightly, though, if I want to find out if a different number is a factor of 25, if I want to find out if, same question, all I'm going to change here is if, I don't know, 2 is 2 a factor of 25. I'm going to again do 25. I'm going to divided by the one I'm checking. 2, I'm going to get in my calculator 12.5, I think. I'll double check that. Yeah, 12.5. This has a decimal part. This is not a whole number. So 2 is not a factor of 25. So that's how we check. We have a number we want to find its factors of, and then I'm going to divide it by numbers I want to see are factors or not. And if it's a whole number, it is a factor. If not, it's not a factor. So with the example given here is 10, right? 10. Let's talk about 10 real quick. Okay, so 10, if I'm checking if 2 is a factor of 10, if I divide 10 by 2, I get 5. So 2 is a factor of 10. One thing that can speed up, we're going to be finding all of the factors. So one thing that can speed this up is if it is a factor, we're going to get a whole number out. And that whole number we get out, in this case, the 5, right? We weren't checking if 5 is a factor. We were checking if 2. But since 2 is a factor, and 5 is a whole number, it's a factor. 5 is also going to be a factor. We could double check that real quick, right? 10 divided by 5 is 2. And we can see that definitely by our definition of what a factor is, this is a factor. But this works every time. This works every time because kind of how multiplication, like I think they call them families, work, right? Is because 2 times 5 is 10, right? These multiples of when we multiply the two factors, these factor pairs, it'll give us back our original number. So these factor pairs always add up, multiply to our original number. So when we find all of the factors of a number, right, I'm going to find all the factors of 10. The way I'm going to do this is I'm going to just start with 1, and I'm going to go, and I'm going to find the pairs. I'm going to start with 1, I'm going to find the pairs, and I'm going to kind of close in on the numbers that we can check. So what I'm going to do is 10 divided by 1. I'm going to see if 1 is a factor. 10 divided by 1 is 10. 10 is a whole number. So 1 and 10 are factors. So I'm going to write them on opposite sides here. And I'm going to count up from 1 until I run out of numbers to check. 1 and the number itself will always be factors, right? Because anything divided by 1 is going to be itself. So 1 and itself is always a factor. So I don't normally actually check this. I just write them down. So now I checked 1 though, and it gave me this pair 10. I'm going to check 2. 10 divided by 2 is 5. So I'm going to write, so it is a factor, and 5 is that factor pair. So I'm going to write it over here on the other end here. Now I'm going to check 3. I'm going to see if 3 is a factor. So 10 divided by 3 is 3.3 repeating. Not a whole number. That's all that matters. I don't care about the repeating thing. It's just not a whole number. So 3 is not a factor. I'm not going to write it down. 10 divided by 4 is 2.5. So again, not a whole number. 4 is not a factor. So we want 1, 2, 3, 4. The next number to check then is 5, just counting up. But we already got 5. We already got 5. In fact, all we need to check is any numbers left between here. And we checked them all. We checked 3, 4, 3, and 4. Those are the only ones left. Once we get to the other end, the other side, this is why I'm doing it this way, right? When I get to the other side, I am done. I don't need to check I don't need to check 5. I don't need to check 6, 7, or 8, or 9. They would have shown up already if they were a factor. So all of the factors of 10 are 1, 2, 5, and 10. 1, 2, 5, and 10 are all the factors of 10. So let's find, yeah. So let's do the practice one first, and I'll go back to the previous slide. So write all the factors of the following numbers. 12, again, 1 and 12, always going to work. 1 and the number itself, always going to be factors. 2, let's do 12 divided by 2, right? That's 6. 12 divided by 2 is 6. So 2 and 6 are factors. 3. 12 divided by 3 is 4. So those are factors. 4 would be the next number to check, but that's already at the other end. There's nothing left to check. There's no more numbers in between. We have found all the factors. These are all the factors. I know it can be spaced out a little bit funny, but that's fine. That's fine. These are all the factors. We are done with 12. 72. I'm going to start with 1 and 72. There might be a lot, so I'm going to go way down here. 72. Comma there. 2. 72 divided by 2 is 36. I'm going to need my calculator for these ones. 2, 36. 3. 72 divided by 3 is 24. Good. So 3 and 24 then. 72 divided by 4 is 18. 4 and 18. 72 divided by 5 is 14.4. That's not a factor. We're gonna move on to 6. 72 divided by 6 is 12. 12. So 6 and 12. 72 divided by 7. That's not a whole number. That's a long decimal point. Not a whole number. Don't care about it. Move on to the next number. 72 divided by 8. 9. That sounds good to me because 8 and 9 are factors. And that means there's nothing left to check in between here, right? There's no numbers between, no whole numbers between 8 and 9. So we're done. These are all the factors. So as we can see, the bigger the numbers are, the factors, there's a lot more factors. And that's almost what we'll talk about. And this is why I'll move on. I'll move on. There's a lot of them for bigger numbers. 7. So like I'm going to start with 1 and 7. And then I'm going to take 7 divided by 2. That's not a whole number. 7 divided by 3 is not a whole number. 7 divided by 4 is not a whole number. And 7 divided by 6 is not a whole number. So these are all of the factors of 7. I went through that one a little bit faster because I know that these are all the factors of this one. Now, 7 is a bit of a special number. It's called a prime number. And we'll talk about some prime numbers in a little bit. So let's go back to the previous slide. I kind of went a little bit out of order here. Previous slide. Divisibility rules. So divisibility rules are useful. They are not necessary, but they can speed things up, right? They're useful in that I don't have to always check these numbers in my calculator. I don't need to do some math to figure out if 3 is a factor. If 3, I can use kind of these rules to speed this up a little bit. And so let's go through them. I'm going to go through 2, 3, 5, and 10. Divisibility rules for 4, 6, and 9 are really just like the same as 2 and 3, just multiple times. So that's why I'm going to skip past them. I don't actually ever really use them. You can learn them if you want, but they're unnecessary. Divisibility by 2 is if so a number has 2 as a factor, it is divisible by 2 if it is even, right? Any even number is divisible by 2. So 26 is even. 26 is even, right? And just as a little recap, right? Any number is even if the last digit on it is even itself. So the even numbers are 0, 2, 6, 8. And so if a number ends with any of these numbers, it's an even number. So 26 ends in 6, that's an even number. So it's divisible by 2. I know this, so I know that when I take 26 divided by 2, it's going to be a whole number, which is 13. When I look at 384, this also ends in an even number. So I know 384 divided by 2 is going to be a whole number. This one I can't do in my head. I probably could, but if I took a second, 384 divided by 2 is 192. 192. And these divisibility rules are nice too, because if something ends in an odd number, if something is an odd number, right? If it ends in 1, 3, 5, 7, or 9, 2, 4. Oh, I forgot 4. I thought that didn't look right. 2, 0, 2, 4, 6, 8. Sorry. Um, if it ends in an odd number, 1, 3, 5, 7, or 9, it's not going to be divisible by 2. So if I have a number like, I don't know, 35, this is an odd number. So dividing it by 2 is not going to be a whole number. You're going to have, it's 17.5, right? This is not a whole number. 2 is not a factor. Odd numbers are not divisible by 2. So let's look at the divisibility rule for 3. The divisibility rule for 3 is a little bit odd. Where'd my mouse go? It's very, very useful because it's hard to look at a number and see if it's divisible by 3. But there is an easy way to tell. And that's what the divisibility rule tells us. It tells us that if we add up the digits and that sum there, the answer to that addition, if that number is divisible by 3, then the original number was, right? So when we add up the digits, it becomes a smaller number. And so with smaller numbers, it's easier to see if a number is divisible by 3. So the example here, 312. If I'm going to take the digits, like each number individually of 312, 3 plus 1 plus 2, 3 plus 1 is 4, plus 2 is 6. 6 is a lot easier to see if it's divisible by 3, right? Because it's 2 times 3. So 3 is 6 is divisible by 3. So that means 312 is divisible by 3. And we can double check that 312 divided by 3 is going to be 104, whole number. So yep, definitely works. And again, so if it doesn't add up to 3, if we have a number like 316, right? This is, if I take 3 plus 1 plus 6, this is 9, this is 10. 10 is not divisible by 3. So 316 is not divisible by 3. So that's kind of the weird one. The next two are are as easy as the divided by 2. The 3 one is a little bit weird, but it helps probably the most. I think most people can tell if it's even, it's going to be divisible by 2. And then for 5, if it ends in 5 or 0, if the last number is 5 or 0. So 45 is divisible by 5. 260 is divisible by 5. If it's a 5 or a 0 at the end, it's divisible by 5. And then 10, if it ends in a 0. And that's all it is for 10, is if it ends in a 0, you can divide it by 10. So there's this. So those divisibility rules are a little bit more helpful in the prime factorization. That's why I went a little bit out of order here. So prime numbers, I mentioned 7 was one, right? So prime numbers are numbers whose only factors are 1 and itself. I put an equal sign. Let's use a colon. These are all the factors of 7, 1 in itself. So it is a prime number. A composite number is just not a prime, basically. And so prime numbers are a little bit tricky to find, because if you can remember how I kind of went through 7, I took 7 divided by 2, 3, 4, 5, and 6, and that takes some time to do. So it is helpful to know like what a few of them are. So I'll write out a bunch. We've got them here, but I'll go further. 2, 3, 5, 7, 11, 13, 17, 19, 23, I think, 29. And they go on forever. There's an infinite amount of them. We don't go too big with our numbers, so this should be enough. And so if you just count in the other ones that aren't on this list, composites, right? So we generally don't count 1 when we're talking about primes and composites, so I'm going to start at 2. So 2, 3, 4 is a composite. 6 is a composite. 8 and 9 are composites, and we can see that we do have multiple factors. I don't know why it's written like this. So the factors of 2 are 1, 2, and 4. Factors of 6 are 1, 3, 1, 2, 3, and 6. Of 8 is 1, 2, 4, and 8. Of 9, 1, 3, and 9. And you can take some time to do that. But what's more important is the prime numbers. Okay, so prime factorization. So now we know what the prime numbers are. We're going to talk about the prime factorization. Prime factorization. This is so prime factorization. Every single number can be written as this prime factorization form. And by what I mean by this is we're going to break down each number into primes. It's going to be a product of prime numbers. Every single number can be broken down into this. Technically, prime numbers themselves can be broken down into it, right? 2 is, I can break it out into the prime just 2. It's a little bit cheeky, trivial, but what's more interesting is the composite numbers in that case. So 72 is the example here. The way I do this is kind of a lot of words. I think it's very much easier if we do the factor tree. 72. So the way we're going to do factor trees, 72. What I'm going to do is find a factor of 72. It doesn't need to be in order at all. And this is where divisibility rules are very useful. So I can tell very quickly what some factors are. And I'm going to take 72 and I'm going to break it down. 72 is even. It's an even number. So I know by my divisibility rule for 2's, 2 is a factor. So I can take 72 divided by 2. It's 36, right? So what I've done here is taken 72 and I've broken it up into 2 times 36. Those are my 2 branches of my factor tree to get me started. Now, anytime I have a prime number, I'm going to be done with that branch of my tree. So I've got this 2, I'm done here. 2 is a prime number. 36 is not a prime number. I know I didn't go all the way up to 36 on my little list here. It's not a prime number. I know it's not a prime number very easily because this is also even. I can write it as 2 times something. 2 times 18. So I've broken down 36 into 2 times 18. Again, 2 is a prime number, so I'm done there. I'm a little ran out of space here, so let's kind of do this. I'm going to break it down like this a little bit further. 18, again, even number. So it's going to be 2 times something. 2 times 9 is 18. 2 is in a prime number. I am done. 9, we can see it was not on our list, and that's because 9 can be broken down into 3 times 3, where 3 is a prime number. So we are done entirely now. All the ends of my branches that don't branch off anymore end in prime numbers. And so now I'm going to gather up all the prime numbers that I found here. And I like to put them in order from least to smallest, least to biggest. Right? So I'm going to see how many 2's I have. I've got 1, 2, 3 2's. Right? So I've got 2, and they're all being multiplied together. 2 times 2 times 2. How many 3's do I have? I have 2 3's. So let's put 2 3's up here. 3 times 3. So this is this prime factorization. And you can double check this. You can take 2 times 2. I'll do it real quick. 2 times 2 times 2 times 3 times 3. And I should get 72 back. 72. I don't know if you can see it. 72. So it's prime factorization. If we remember what we talked about exponents, we're kind of going a little backwards here to just make it a little bit neater is nice sometimes. So I'll write 2. There's 2 times 2 times 2, 2 times itself 3 times. So that's 2 cubed, 2 to the 3rd, and 3 squared here. So just to clean it up a little bit, you can write it that way. 2 cubed, 3, and 3 squared. So let's see factorization trees. So here's the actual slide for factorization trees. So let's go through each of them real quick. We've got 3 different numbers. I'll start with the 36 here. 36. This one, so we can break up 36 into 9 times 4, right? 9 times 4 is 36. So they broke it up into 9 and 4 here. I personally would have broken up into 2 times something because it's a bit easier to see that uh, it's even, and so 2 will be one of the branches. So these factor trees aren't unique, but they are always going to end in the same primes at the end. So I'll do 36 as it's shown, and then I'll show you how I probably would have looked at it. 36 can be broken up into 9 times 4. 9 is not prime, so let's break that one up. That is 3 and 3, which are primes. So let's go back to 4, which wasn't prime either, so we need to keep going with 4, which was 2 times 2, which are all primes. So this is 2 2s, 2 times 2 times 3 times 3, 2 3s as well. Now, like I said, I'll do 36 myself to show how I would do it. Right, I see 36 is even, so I would have done 2 and 36 divided by 2 is 18. This is done here. 18 is again even, so I would do 2 times 9, which is 18. 2 is done. 9 can be broken up into 3 times 3. And we can see here at the bottom, obviously the nice and even at the bottom with when that was typed in. 2 3s and 2 2s, 2 2s and 2 3s. So it does work no matter which way you approach it. So they're not, you could have different trees, but you're still always going to get the same answer. So 220. I'll do 220 myself as well. So 220, this is even. So we can break it up into 2. 220 divided by 2 or 2 is 110 or 210. I'm sorry, 2 times 110 is 220, however you want to think about it. 110 is even again, it ends in a 0, so it's even. So you can pull out another 2. 110 divided by 2 is 55. One little divisibility rule that I didn't talk about here. 55 can be broken up into 5 and 11. 11's prime, so that does bring it all together here at the end. What I was going to say here real quick is, so if you have a 2-digit number, so this only works with 2-digit numbers, like 22, 33, 44, 55, 55 being an example here, is going to be 11 times whatever that double number is. So the number 22, that's 2 and 11. The number 88, this is 8 and 11. So that's another, like, divisibility. It's not a hard rule because it only works for 2-digit numbers, but it's useful for you guys because we're working with small enough numbers that a lot of the times 11 will be an easy one to spot. Again, I'll do the way I probably would have done it. I see 220, and I would use the divisibility rule for 10, right? This ends in 0. So I know it's 10 times something. 10 times 22. So let's break down 10. 10 is 2 and 5. 22, this is again that double digit thing. So 2 times 11. And we see we 2, 5, 2, and 11. So 2 2s, right? 2, 5, 2, and 11. That's how we can break down 220. 864. Again, it's the one this is drawn here, right? It's very hard to see that 32 times 27 is 864. In fact, I have to double check that. It's true. So you could, if you do somehow see that right away, you could start off with those numbers. So honestly, I'm not even gonna go through it as that. I'm gonna go through it how I would do it. This is even 2. 864 divided by 2. This is 432. This is also even. I'm gonna pull out another 2. I'm gonna try and make sure I have enough space here. 432 divided by 2 is 216. This is even again. I'm gonna put 2 on this side so I can kind of work my way back that way. 216 divided by 2. 216 divided by 2. 108. Even again. 2. 108 divided by 2. 54.
even again, another 2. I'll put it on this side now. It doesn't matter which one you put it on. 54 divided by 2. 27. 27. Finally, an odd number. We can't pull out any more 2s. 27, if you don't see it right away, it's 3 times 9, but you could always just do 2 plus 7, right? The divisibility rule for 9 is, not for 9, for 3 is you add up the digits. So it's 27, I'm adding 2 plus 7, which is 9. 9 is divisible by 3. So I can do 3 times 9. And we've seen 9 already. This is 3 times 3. So let's see. Let's see what they got and double check our answer, right? They've got 1, 2, 3, 4, 5 2s. 1, 2, 3, 4, 5 2s. Yep. And they got 3 3s. 1, 2, 3. So yeah. So like I said, this is how I would have done 864. This is a crazy thing to figure out right off the bat. It's much easier to see that 2 works. And you can, sure, it's a little bit longer, but it's a lot easier to do. Because then they also break up 32 into 4 times 8. I would have broken it up into 2 again because it's even. But 4 times 8 is 32. And then let's just look at it. 4 is 2 times 2, 8. This, yeah. I honestly don't know why they use this tree here. 8 is 2 times 2 times 2. You can see that, or you can do 2 times 4 and then break up 4 into 2 times 2 itself. This is how we broke up 27. So 3. They drew a little line just so it all lined up to 3 again. 9 is 3 times 3. So again, this tree is a little bit crazy. I'm gonna try to get rid of that one. This is how I would do it. Practice. So 540. I'm gonna draw my little tree. This ends in a 0, so I know 10 is a factor. So 10 times 54. 10 is not too bad. That's 2 and 5. 54 is even. So 2 times 27. So I should know. We're done with all these spots, right? And then 27 is divisible by 3. We saw this one a second ago. If I do 2 plus 7, it's 9. That is divisible by 3. So 3 is going to work. And it's 3 times 9. That's done. And then 3 and 3 again. The prime factorization, let's write it out. How many 2s? We got 2 2s. 2 times 2. We've got 1, 2, 3. 3s. And 1 5. We have a 5 as well. This is its prime factorization. For now, I'm not going to rewrite it with the exponents because I'm going to want it to be that way. Sorry, I thought I heard someone. 231. This one's a little trickier. It's not even, it doesn't end in 0, it doesn't end in 5. The next number I would check though is the divisibility rule for 3. So 2 plus 3, just adding up the digits. 231. 4, 6. 6. So I add up the digits. This is 6. This is divisible by 3 because 6 divided by 3 is 2. So I know 3 will work. And then I need my calculator to figure out what 231 divided by 3 is. 77. 77. And this one's a little bit easier to see, right? This is that double digit number. 7 and 11. 3 is a prime, 7 is a prime, 11 is a prime. Again, 11 we haven't seen as much, but it is a prime. So 231 is 3 times 7 times 11. So equivalent fractions. Yeah, equivalent fractions. Fractions represent. So a fun thing about fractions is that we can write them as different numbers, but they have the same value, right? Similar to how we had mixed numbers and improper fractions, we wrote it 2 different ways, but they were the same number essentially. They still represented the same amount of circles.
So equivalent fractions are same idea, just with normal fractions, not throwing in mixed numbers in there at all. Equivalent fractions, same value, just different numbers. So if we look at what we have here, we've got a circle split up into halves, right? The bottom tells us how many equal parts, so 2 equal parts, and you have one of those equal parts. If we have that same circle and we split it up into fourths, into 4 equal parts, and you have 2 of those equal parts, you have 2 out of 4. Look at these two circles. You have, in both cases, half of the circle, right? You have the same amount of circles. So even though 1/2 is different than 2/4, these represent the same value. These are equivalent. And then same thing with 4/8, right? We're splitting it up into 8 equal parts, and you have 4 of them. You have half of the circle. So 1/2 is the same as 2/4. 1/2 is the same as 4/8, and so on. One way to easily check if 2 of them are equivalent is this cross multiply thing. I don't ever actually do this, but I'll talk about it since it's on the slide. Cross multiplying. If you say two fractions are equal to each other, you take the top of one times the bottom of the other. In this case, 1 times 4. And then same thing with the other ones, right? Top of the other one times the bottom of the first. 2 times 2. 4 equals 4. So they are equivalent. So it's a quick, easy way to see if they're equivalent. And what I'll say here as well, too, before I move on, is to get an equivalent fraction, all you need to do is multiply the top and bottom number, the top and bottom of the fraction, by that same number. So if I ask myself, how do I go from 1/2 to 2/4, I'm multiplying the top and bottom by the same number times 2. 1 times 2 is 2. 2 times 2 is 4. If I want to go backwards, I can divide. So how do I go from 4/8 to 1/2? If I divide the top by 4 and the bottom by 4, you can see that's 4 divided by 4 is 1. Good. 8 divided by 4 is 2. Now going backwards is this idea of simplifying the fraction. So it's in a simplified fraction is equivalent fraction, but the division is a little bit trickier. So I'm going to go through a different way to do it first, because I think this is the best way to do it with this prime factorization idea. It's the most foolproof way. And with the other ways, there's easy ways to maybe not reduce all the way. Maybe you miss something. I think this is the most foolproof way to simplify the fraction. And all we're going to do is we're going to have a top and bottom of a fraction, right? Say we have this fraction, -170/10. I'm going to find the factor trees of the top and bottom, right? The top is 170 and the bottom is 110, right? So I'm going to find the factor trees of both those numbers. I'm going to get the factorization once I do that. So let's quickly do that. Let's walk through it, right? 170, 10, right? Ends in 0, so 10's a factor. 17 times 10. 17 is a prime number. I'm not sure if that made it onto my list, but 17 is a prime number, so we're done with that. 10 is 2 and 5. So just for my sake, too, I like to write them in order. So I'm just going to rewrite this 2 times 5 times 17. You don't have to. This is fine. I always do it this way, though. 110 is an even number, so they split it up into 2. And 55 is that 11 one, right? 11 and 5. So this one they wrote in the order I like, 2 times 5 times 11. So I've got my fraction that I'm trying to reduce. To rewrite it, right, this is a negative, as I'm going to rewrite it, each of those numbers with its prime factorization. So the prime factorization of 170, the top, was 2 times 5 times 17. Of 110 was 2 times 5 times 11. So now that I've done this, this is where the fun begins. So if we remember, anything divided by itself, anything on top of itself was 1. And we're following this rule here, right? If there's something on the top and bottom of the fraction, it becomes a 1. It cancels out and becomes a 1, right? So with my prime factorizations back down here, I've got this 2 on the top and this 2 on the bottom. I'm going to cross them out. I don't put a little 1 there. I see a 5 on the top and bottom. I'm going to cross this out and put a little 1 there. They get canceled out. I can't do that with the 17 or 11, right? There's no 17 on the bottom to cancel out. There's no 11 on the top to cancel out. So this simplifies here. Let's do negative 1 times 1 times 17. Just rewriting it 1 times 1 times 11. And then we're just going to multiply this all out. All right, 1 times 1 times 17 is 17. 1 times 1 times 11. Oh, I forgot my negative sign at the beginning. Negative. 1 times 1 times 11 is 11. So simplifying this fraction or reducing it to lowest terms, reducing a fraction to lowest terms, simplifying, same thing, just another word for it. Negative 17 over 11. Right, and so I went through, I took the top and bottom, found their factor trees, rewrote it with their prime factorizations, and then canceled out. We can see with what was typed in here, they just crossed them out and didn't write them with 1s. That's what I will do most of the time. But it's helpful to remember that it's 1s that I get replaced with. So once I cross out the 2s and the 5s here, what I have left is that 17, and what I have left is that 11. So 17 over 11. Because multiplying by 1 doesn't change anything, so a lot of times I don't write the 1. But let's go on to the practice problems. Yeah. So 540 and 924. So we're going to simplify these fractions. We're going to reduce them to lowest terms. We're going to take 540. We're going to find its prime factorization. I'll write 924 up here because that's what we're also going to find the prime factorization of. Ends in a 0, so I know 10 will work. 540, 54. 10 times 54 is 540. 10, we'll see 10 a lot. So 10 is 2 and 5. That's not a bad one. 54 is even, so I'll pull out a 2. 27. 2 times 27. 27 we've seen a couple times already. This is 3 as a factor. 3 times 9. And then 9 is 3 times 3. So let's rewrite it. This is 1, 2. So 2 2s. How many 3s? 3 3s. 1, 2, 3. These are times. And 5. Times 5. I'll write it over here. I should press the time symbol so it doesn't look like 22. 3 times 3 times 3 times 5. And now I still need to find 924. This is even, so I'm pull out of 2. 924 divided by 2. 462. All right, 462. This is even again. 2 is going to be a factor. 231. I think 231 we saw already. But if you don't remember, it was divisible by 3. It's not. This is one that's harder to see because it's not even. Divisible by 3, right? 2 plus 3 plus 1 is 6, which is divisible by 3. So 6. I'm sorry, 3. So what's 231 divided by 3? 77. And we've seen the double numbers a couple times now. 7 times 11. So because I ran out of space, I'm going to go right into the fraction writing it. So how many 2s? 1, 2. 2 2s. How many 3s? Got 1 3. Got a 7 and 11. That's left, right? So 7 and then 11. Got a little line just so I underline everything. Now I'm canceling out. There's a 2 up here and a 2 up down here. There's a 2 up here and a 2 down here. There's a 3 up here and a 3 down here. Can't do anything with these 3s. There's no more 3s to cancel with at the bottom. Can't cancel this 5. Can't cancel the 7 or this 11. So at this point, we could rewrite. We could do it. We could just do the 3 times 3 times 5, or
the 7 times 11 on the bottom. I'm going to rewrite it so it's a little bit more clear. Just rewriting it where I'm leaving off all of the things I crossed out. So 3 times 5 on top, and 7 times 11 on bottom. And so now the last step here is to just multiply these out to go back to just a single number. So 3 times 5, 45. 7 times 11 is 77. So this is my answer. Right? So these two fractions are the same. 45 over 77 is just has smaller numbers, but they have the same value. If I were to take circles, if I were to take a circle and split it up into 924 equal parts, and I had 540 of them, that would be the same amount if I were to take the circle and split up into 77 parts and have 45 of those parts. Okay, I am gonna delete here so that I can do the factor trees of 26 and 54. So I'm gonna delete my trees. If you want to write this, so writing those down, take a second, pause it, but I'm gonna delete them now. Okay, so again, I'm simplifying. I want to find the factor trees of 26 and 54. This is even. 2 times 13. 13 is a prime number. I think 13 is one we haven't seen yet. It's a prime number. We're done with that one. 54. 2 is even. So I'm pulling out 2. 2 times 27. We must have seen this one before. At least the 54. 27 is 3 times 9. And the 9 is 3 and 3. So now, just to save some space, because I don't want to delete this one, is I'm going to go right into it. 26 is 2 times 13. 54 is 2 and then 3 threes. 2 times 3 times 3 times 3. I'm going to cross out the 2 with that 2. So I'm left with this 13 over 3 times 3 times 3, which is 27. So this is my fraction reduced. 750 and 3 over 375. And we get rid of the factor trees again, so take a second if you need them still. So this one thing I'll note too is note that this is an improper fraction. We still need to reduce improper fractions. It does not matter that the top is bottom. We do the same exact thing. $750 ends in a 0, so I can pull out a 10. 10 times 75. So 10 is 2 and 5. We're done there. 75 ends in a 5, which is that rule we haven't seen very much. But I can pull out a 5 though. 75 divided by 5 is 15. And again, this ends in a 5. Or you could add up 1 plus 5 is 6 and see that 3 is the other factor. It's 3 times 5. So 750 is 2 times 3 times 2 times 3 times, and then we have 3 5s. 1, 2, 3. Those two 375. This one ends in a 5. So it's going to be 375 divided by 5 is 75. Oh, this is going to be the same exact branch here, right? Ends in a 5. So it's 5 times 15. And 15 is 3 times 5. So we have, what do we have? 3 and then 3 5s. 3 times 5 times 5 times 5. So now I'm canceling. We have nothing cancels with the 2, right? The 2's on the bottom, but I can cancel this 3. I can cancel this 5. I can cancel this 5. I can cancel this 5. What's left here? 2. 2 on the top. Again, I don't have anything left on the bottom.
this is why I still wanted to point out that when we cancel them, they do get replaced with ones. Technically, don't write 0 here, right? Even though there's everything got crossed out. When they get crossed off, they get replaced with ones. It's 1 on the bottom. You can do 1 times 1 times 1 times 1. Anything times 1 is 1. All these ones multiplied together is going to be 1. So it's 2 over 1. Anything divided by 1 is itself 2. 2. So it ended up not even being a fraction at the end, right? You could have, if you've seen this right away from the start, like with that one long division problem, it's possible to see this from the start. It is, you can, 750 divided by 375 will be 2. But if you didn't see it right away, this is how you do it. And that's why I just went ahead and did it, even though I knew that was going to be the case. I believe someone wanted to asked about doing it, simplifying another way. I'll cover another way right here. I don't really recommend doing it this way because it's harder to tell when you're done, but I'll do this because I know some people have seen it this way. There's lots of different ways to simplify. There's 3 main ways, this being one of the main ones. This one is a little bit harder because it's hard to tell when to stop. And by that, I mean, we'll see what I mean by that. So with 540 over 924, what I'm going to do is just find a common factor, a factor that is a number that is a factor for both of them, right? And this is going to be following that idea that I'm going to divide by that same number. But the way I do it is find the common factor. So I can see that these are both even numbers. So my divisibility rule, it tells me that it's 2 times something. Or if I do 540 divided by 2, I can see what that number is. So I know it's 2 times something. What is 540 divided by 2? 270. And 924. 924 divided by 2, 462. And now I'm doing my cancel here, 2. I can cancel out a 2. Right, it's on the top and bottom. But I'm not done yet, right? This isn't that same answer we got. That's because there's more factors that I can cancel out. And I'm just going to do this step by step, right? They're both even again. I'm going to pull out another 2 out of both of them. 270 divided by 2 is 135. 462 divided by 2 is 231. Do they have any more common factors? That's the tricky part of doing it this way. The answer is yes, right? And I know because I can do the divisibility rule for 3, right? 1 plus 3 plus 5 is 9. So I know 3 is a factor, so I can pull out a 3. And 2 plus 3 plus 1. This is that same one again with the divisibility rule for 3 is 3, right? 2 plus 3 plus 1 is 6. So 3 is also a factor here. So 135 divided by 3 is 45. 231 divided by 3 is 77. Cross out the 3's. And is there any more steps here? Let's see. This is where the problem gets tricky, and this is why I don't do it, because now I have to think of, still have to break these down essentially in some way. But these can't be broken down. There's no more common factors in it anymore. In it. The factors of 77 are 1, 7, 11, and 77. 45 has 1, 3, oh man, 9. Some other ones, I without writing them down, it's taking me a second, but you will see that they do not have any more common factors other than 1. It needs to be bigger than 1. If I pull out a 1, I'm not changing the numbers. I don't want to change the numbers, otherwise I'm not doing anything. So 45 over 77, and this is why I don't love this way. I just pull them out, and it's hard to know when you're done. because that's not immediately obvious that 45 and 77 is as far as we can go. Yeah, I'll leave it at that one as kind of a refresher for those who wanted to see a method, one with that method. Okay, so we talking about this canceling the top and bottom, which is again the same thing that I did here. We cancel out the top and bottom, and I cross them out. We can do those with letters as well, right? So with this 10x squared yz and 15xy to the fifth, I am writing out those, I'm expanding the exponent, right? X squared is x times x, right? It's just telling you how many times we're multiplying it itself. This y to the fifth means it's y times y times y times y times y 5 times, right? Because the power is 5. And I'm canceling out things in the top and bottom, right? So this step expanded them. It also wrote the prime factorization of the numbers. So it canceled out this x with this x. Lines aren't very clear. This y with this y can't cancel out any more of the numbers, but with the prime factorization, we can cancel out the 5. I normally do this in 2 steps. I normally look at the letters first and then clean it up and then do the prime factorization trees to do this part. This does it all in one step, which is fine. But we can see here, once we do that, we've got 2, we've got 1 x left, and we've got a z. We've got a 3 left, we've got 4 y's, so it's 3 to y to the 4th, cleaning it all up. And so this idea of cancellation, it applies, we're going to talk about multiplication in a second, so that's why I'm going to skip over this real quick, vaguely skip over it. The idea is when we multiply, we're going to go straight across. So essentially, these are already in the top and bottom, even though they're in 2 different fractions. But when we multiply them, they will be in the same fraction. And we could do it with units, right? So this ml is not an M and a capital L. This is milliliters. And this idea of canceling out the units will be very helpful in ensuring we're setting up all the problems correctly later on, about week 3 or 4, or I guess probably week 4. So yeah, milliliters in the top, milliliters in the bottom. They get canceled. This ounces here, this OZ is ounces. There's nothing that cancels out. It tells us that our answer, that's the only unit left. So our answer will be in ounces, but I'm going to pass over it for now. We'll see these more often later. Okay, simplify the following fractions. So I'll do this first one again. The second one, again, all I want to know here is I'm going to be canceling out kilograms. Pounds is going to be my answer, but important part is canceling out kilograms. So let's look at the first one though. 2a squared b5 b to the 5th over 6a cubed b cubed. I'm going to expand. I'm going to do this not all in one step. I'm going to do it with the letters first and then the numbers. So I'm going to keep the numbers for now. I'm going to kind of ignore them, but they're still following along. So 2 over 6. And I'm looking at the numbers. So a squared, that's a times a. I've got b to the 5th. So this is 5 b's. 1, 2, 3, 4, 5. And I've got 3 a's on the bottom. 1, 2, 3. And I've got 3 b's on the bottom. And I'm canceling now. All right, I've got this a cancels with that one. This a cancels with that one. Can't do anything with this a, so let's go to the b's. This one cancels. That one. And this one as well. Can't do anything else with these leftover b's. So let's clean this up for a little bit right here. 2, and I'm just getting rid of all the things I crossed out just to clean it up. And 6a on the bottom. Now I'll clean it up one more time. I'm going to turn that 2 b's into b squared. Oh, forgot my 6 on the bottom. And now I got to deal with the number part. So I dealt with the letter part. Now I got to deal with the number part. I got to do the factor trees. 2 is already prime. There's actually no, that is the factor tree is just 2, right? It doesn't have any branches. I can't break up 2. I could write 1 and 2, but again, that's I don't want to write 2 in my, or 1 in my factor trees because that doesn't change anything. What was the other number? 6. 6 was 3 and 2. So let's put the numbers part where we broke it up into our prime factorization. Again, the prime factorization of 2 is 2. And 6 was 3 and 2.
Now I'm kind of ignoring the letters, but they're coming along for the ride. And this 2 cancels. So now all that is left is b squared on top and 3a on the bottom. And this is my final answer. Nothing else will cancel. This is the simplifying of the fraction with variables in it, with letters. Hold on. What time is it? Let's keep going. Applications of simpling fractions. So we've got this word problem. Lisa and Lynette are taking courses online. They've completed 14 out of 16 assignments in her course, and Lynette's 15 out of 24. What fractional part of her total assignments did each woman complete? And so the idea is to be able to compare these, how much of each one they completed. They need to have the same bottom, which we'll talk about a little bit later. But the way this problem is designed is that when we simplify these fractions, that they will have the same bottom, and it'll be clear. So let's simplify these fractions here. So 14 turns into 2 times 7, and 16 becomes 2 times 8, which becomes 2 times 4, which becomes 2 times 2. Again, I'm just using the divisibility rule for 2, essentially. It's even, 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 even. So 14 over 16 becomes 2 times 7. 16 becomes 2 times 2 times 2 times 2, 4 of them. 1, 2, 3, 4. And one of these 2's cancels out. What the? To the top is 7. The bottom is 2 times 2 times 2, which is 8. 15 over 24. So let's see, 15. This is 3 times 5. 24. This is 2 times 2 times 12. Becomes 3 and 4. I know I'm going into my mad scientist a little bit, but I'll draw my lines out. 2 and 2 again. So 15 over 24 is 3 times 5 over 2 times 2 times 2 times 3. This 3 cancels out. 3 at the top and bottom. We have 5, and then 2 times 2 times 2 is 8. So Lisa completed 7/8 of the course, and Lynette finished 5/8 of the course. Now that they have the same bottom, we just compare the tops, right? Lisa did more of those eighths. So she completed more of the courses. So again, I'm going to draw a couple circles here to represent what we have. We simplified the fraction into essentially, right, classes, which I'll represent as the circle, into eighths. And Lisa did 7. So 1, 2, 3, 4, 5, 6, 7. So only missing that one little part. And Lynette did 5. 1, 2, 3, 4, 5. So clearly, Lisa completed more of her circle, which represents the class, than Lynette did. The second example, I'm going to skip over this one because to simplify, it takes a while to simplify, when in reality, all you really need to do is 25,000 divided by 500, which we'll talk about, I think, in week 3, we'll do the similar ones. Multiplication and division. So this is why I skipped over one of the problems, because we actually haven't talked about multiplication and division of fractions. Okay. So multiplication is real simple. We just go straight across the top and bottom. Okay. So let's see what we got here. And so let's look at this one first. Yeah, let's look at this one first, right? We've got, they don't have a basic example on this one. Let's do a basic example one. So I'm making up some numbers. 1 over 2 times 3 over 4.
and I go straight across. 1 times 3 is 3. 2 times 4 is 8. Right, just straight across. We've got this example here, right? This -7 over 12 times 11. When I do this multiplication with fractions, I want them to all be fractions. 11 is just a number, but I can always put it over 1, right? Because 11 over 1 is just 11. Dividing by 1 doesn't change it. I could always just put it over 1, which is what they do in the next step here, you can see. And so -7 over 12 times 11, straight across. We get 77 over 12. And we've got this negative sign at the beginning, right? This is one negative sign. This is going to be a negative number. So 77 over 12. This one, similar idea in that we don't have two fractions multiplying by each other, but instead of just the whole number like 11 was, this is a mixed number. So we need to turn it into a improper fraction. We're going to do that just because I just want a top and bottom. I don't want anything out in front. I just want top and bottom. So I don't want this. It gets complicated if you try to do this, and we're not even going to go over how to. So we're going to turn it into an improper fraction, and that'll solve this problem. So it's if you remember, it's 2 times 5, 2 times the bottom plus the top. 2 times 5 is 10 plus 3 is 13. You can see the 13 there. And we keep the same bottom, 5, 13 over 5. So we change it to an improper fraction, and then we multiply straight across. That's how we multiply. Bing, bang, boom. 13 times 1 is 13. 5 times 2 is 10. Note that in this example here, the fractions are both negative. Two negative things being multiplied means that the answer is going to be positive. So that's why it's positive 13 over 10. And if we look at this third example here is telling us that we need to make sure we reduce. Okay, so we multiply, this is honestly, in my opinion, skipping a step or two, right? So I'm gonna multiply them straight across. I'm gonna write what that is above. So 6a squared b cubed over 4ba. I'm gonna swap b and a. Just I can do that. I'm allowed to do that because I like them and I'm doing it because I like them in alphabetical order. It's not necessary, but it makes things easier. And then, so we get to here first, and then we'll go down to here. So multiplying straight across the top and bottom, and then you gotta simplify. That's all this next few steps is simplifying, right? Expanding the exponents, finding the prime factorization, which is 2 times 3 and 2 times 2 respectively, and then starts canceling out things. And then cleaning it up. That's all that one is. So let's look at some examples. So we just have some numbers in our examples. Usually we just have numbers. So multiplication of fractions, just straight across. 11 times 7 and 13 times 5. So 11 times 7 is 77. 13 times 5 is the 65. Now, again, we should double check that these are reduced, that they are simplified. I'll save us some time for these ones because I've been talking a while, an hour and a half. I'm gonna save us some time, and I'm going to tell you this one is reduced. If you're not positive, you can do the factor trees yourself. I'll leave that one as an exercise. So this one, we've got the mixed number. I don't want mixed numbers. I just want normal fractions. So 3 times 2 plus 1 is 7. Keep the same bottom, 2. So I've changed this 3 1/2, that's 7 over 2, and now I'm just going to rewrite the rest of it here. 7 times 4 is 28. 2 over 9 is 2 times 9 is 18. This can be simplified. This will be simplified to 14 over 9. This is going to be 1. This is going to be 1. Okay. I can see this right away because I can cancel out right away. Right? Everything cancels out. So it's going to be 1s over 1 times 1 over 1. But if you don't see that right away, we see 7 times 7 is 77. 7 times
I'm sorry, 7 times 11 is 77. 11 times 7 is 77. Let me erase that one so I can do a little bit better than that's what we're doing here. And then you could break it down with this prime factorizations and see that everything will cancel out like it did originally. But or you can just note that anything divided by itself is 1. It's going to be 1. Reciprocal. So reciprocal, there's a lot of stuff on the slide. The reciprocal is you just flip the fraction upside down. So reciprocal of a fraction is you flip it upside down. So if we have a fraction 1/3, the reciprocal is 3/1. We're going to flip it. I'm not even going to go any further into this. It's just you flip the fraction. Because so division of fractions though. Division of fraction, what we're going to do is going to when we're trying to divide fractions, turn it into multiplication. Multiplication. Put a little a. We're going to do that by keep change, flip. Keep, change, flip. But I'll explain that in a second. So once we turn it into multiplication, by keep, change, flip, 2, we multiply. Like normal. We just went over multiplication. Multiply is just straight across the top, straight across the bottom. So turning it into multiplication. We've got this here. We've got it with letters. I like to do it with numbers because I know a lot of people don't like the letters in math. So if I do 1/2 divided by 1/3, sure, 1/3, why not? I'm going to keep, right? So this is keep, change. I'm going to keep the first one. By keep, I mean just keep it as is, 1/2. I'm going to change the sign. I'm going to change this from division to multiplication. And in order to do that, I need to flip the second one. 3/1. So I keep, I change, I flip. Keep, change, flip. And now it's just a multiplication problem. So now it's just 1 times 3 is 3. 2 times 1 is 2. That's all it is. So again, we've got a couple other examples here. We'll go through the practice ones. The other tricky one though is a complex fraction. So we talked about proper and improper fractions. This is something called a complex fraction. It is a fraction whose numerator or denominator is a fraction itself. So whose top and bottom is a fraction. So we can see like this is the main middle of a fraction, but the top of it is a fraction and the bottom is a fraction. When we see this, there's a bunch of letters in here, so I'm going to simplify it a little bit into 1/2 over 1 over 3/4. We'll do that. The way we solve this is just remember fractions are division. So it's I'm thinking about the middle one as the fraction here. I don't know why I did that. So it's the top divided by the bottom. So it just becomes 1/2 divided by 3/4. Right? That big fraction line in the middle is what I changed into a division sign. And now this is just division. This is just division, right? Keep, change, flip, multiply. 4/6. Which this can be reduced. This can be reduced again. I'm going to skip over a little bit. 2/3. So in all these problems, now that we have gone over reducing and simplifying, we should always make sure that our answers are simplified. So let's do the practice ones. 3/2 divided by 5/11. So keep, I don't know, I'm waiting on some answers. It's just me. 3/2, keep, change, flip. 33/10. This can't be reduced. We'll move on. Be careful with this one. Right? This is not something divided by itself. It looks that way. Your eyes are brought to it to think that, but it's not quite right. But we have this number. I like to do my math with fractions. So 1/2
I'm just rewriting so far, divided by 2 over 1. I can always put that over 1. And now I'm going to do my keep, change, flip, 1 over 4. 1 times 1 is 1, 2 times 2 is 4. And now here's the complex fraction, right? I'm taking this main middle fraction line and turning that into division. 3 over 5 divided by 7 over 11. And now I'm going to keep 3 over 5. I'm going to change the sign, and I'm going to flip the second one. This turns into 33 over 35. This one also, we are good. This doesn't get simplified anymore. You can double check that. Okay. I am going to skip over these slides. They're not important. Least common multiple. Okay, so this is where things got messy, okay? But I have gone through the homework assignments and the exam. And so I'm going to do this the easy way. And I'm going to skip over the hard way, okay? I'm going to skip over the hard way. Because it doesn't matter. And the hard way is there because of I hope everything's all right. Give me 1 second.